Hello everyone and welcome to another video in our microprocessor architecture discussion. Today we are continuing with processors, memory, and peripherals. We're going to make a very brief discussion about each of these parts. So what is a processor? Obviously we're dealing with microprocessors, so we have to know what a processor is. Well, a CPU, also known as central processor or main processor, is the most important part in a given electronic computer. Its electronic circuitry executes instructions of a program such as arithmetic, logic, control operations, as well as input-output operations. This role contrasts with that of external components such as the main memory in the input-output circuitry. And you can see to the right of the screen how a processor looks. What you see here is an Intel Core i3 processor. Of course, the term CPU now refers almost exclusively to microprocessors. They are manufactured on a very small number of integrated circuits, which allows for faster switching time because of physical factors like decreased gate parasitic capacitance. Basically, it allows for improved information transmission speeds, and generally microprocessors are very fast. This allows synchronous microprocessors to have clock rates from tens of megahertz to several gigahertz. The first widely used microprocessor was made by Intel in 1974, and it is called the 8080 microprocessor. And you can see here in this picture, this very first picture here, how this 8080 microprocessor looked like. You can see it's very small. It has a couple of pins on each side, and at the very center is the processor itself. During this presentation and the rest of our discussion about microprocessors, we will focus on the 8086 microprocessor, which is a 16-bit microprocessor chip designed by Intel between 1976 and 1978, when it was eventually released on June 8, 1978. The 8086 gave rise to the x86 architecture, which eventually became Intel's most successful line of processors. And you can see here at the bottom of the page just how an Intel 8086 microprocessor looks like. Again, lots of pins on either side, and the processor, it's in the center. We're going to discuss about the structure of this microprocessor and how it works. We're going to learn to program it, to run applications using this microprocessor. And basically, if you learn how to use the 8086 microprocessor, then you can apply that knowledge to later processors that came after the 8086. And you see that the architectural designs of most microprocessors change, and this change is very drastic as there's new technology appearing every year, and every 10 years the number of transistors within a processor is doubled. So then you see they get a lot more complex as time goes on. The 8086 microprocessor is very simple and easy to understand if you can take the time to actually learn how it works. You have on the left side here an pin kind of diagram of the 8086 CPU or microprocessor, and there are a lot of pins which we will learn about later during our discussions. All internal registers as well as internal and external data buses are 16-bit wide, which firmly establishes the 16-bit microprocessor identity of the 8086. What you should take away from this slide is that the 8086 is a 16-bit microprocessor architecture. So that's something that you should keep in mind. And here are Intel 8086 registers. We're not going to focus on any of these registers right now. We will, though, in 2 or 3 videos time, when we're going to start discussing about each of the main registers, the index registers, the program counter, segment registers, as well as the status register, and what each of these do, and what role they have in a microprocessor architecture. Moving forward, we have a discussion about memory types. The memory inside our computers is usually divided in 2 parts. There's the primary memory, which the CPU can access directly. Here you have as examples the random access memory, or RAM, which is a short-term memory where only the data currently in use by the CPU is kept, or the read-only memory, which is non-volatile and connects by electronically modified post-manufacturing. We'll see what that actually means. Then there's the second memory, which is a long-term persistent data storage that's not directly accessed by the CPU. This includes hard drives, solid-state drives, optical CD or DVD drives, servers, tape drives, storage devices, cloud storage even. All these are considered as second memory devices that can store data for a long time and do not have to be directly accessed by the CPU. Here we have a couple of examples of actual memory devices. We have top left corner, the RAM, or as we know it, is the random access memory. At the bottom left, you have the ROM, which is known as the read-only memory. And to the right of the screen, you see the static RAM and dynamic RAM. So the random access memory is divided between 2 kinds. There's the static RAM, and there's the dynamic RAM, SRAM and DRAM. SRAM has a lower access time, so it's faster compared to DRAM. It is more expensive than DRAM. It requires a constant power supply, which means this type of memory consumes more power. Due to complex internal circuitry, less storage capacity is available compared to the same physical size of DRAM, and also SRAM has low packaging density. And DRAM, as opposed to the SRAM, has a higher access time, so it's slower, but costs less as compared to the SRAM and offers reduced power consumption due to the fact that the information is stored in capacitors. Due to small internal circuitry in the 1-bit memory cell of the DRAM, the large storage capacity is available, and it has a high package density. Most modern computers use dynamic RAM because they are cheaper to use as main memory. You will find SRAM memory types used as cache memories. Then you have the hard drives. Basically, almost all desktop computers have a hard drive. So you can see how a hard drive looks like. You have the image of a 4 terabyte Barracuda storage capacity hard drive, and the internal workings of an actual hard drive and how it works. You can see there are a lot of elements here, and I'm not going to go into how a hard drive works. Just to show you that this is a kind of permanent storage memory that can store a lot of information. You have the solid state drives, and you have CDs, DVDs, and then there's the USB or flash drive sticks, which can also store information. Also have a microprocessor inside them, and there are USB drives of different sizes, ranging from, I don't know, 2 gigabytes to 32 gigabytes. So this is also a storage device. Basically, everything you see here on this slide and on this slide are storage devices. The RAM and ROM being primary memory devices, and the others are secondary memory devices. Now, of course, we talk a lot about memory capacities in certain devices, laptops, computers, whatever. So when we talk about the size of or the capacity of a device to store information, we um, refer to the byte size of that device. And here are some useful quantities that you should know. There's byte, kilobyte, megabyte, gigabyte, and terabyte. You can see how many bytes each of these have. Like 1 terabyte is 1 quadrillion bytes. That's a huge number. What you should remember is the abbreviations for each unit and roughly how you can express each unit in powers of 2, because we work with powers of 2 here. So, for example, a kilobyte is 2 to the power 10 bytes. 1 megabyte is 2 to the power 10, everything to the power 2 bytes. Or 2 to the power 12, if not I'm mistaken. And so on and so forth. And you have after this the peripheral devices. So we discussed a bit about the memory, how there are many memory devices that can store information, some of which are more important than others, some of which are faster than others, and so on. In terms of peripheral devices, a peripheral device provides an input-output function for a computer and serves as an auxiliary computer device without computing-intensive functionality. The peripheral devices connect with the computer through several input-output interfaces, such as communications, COM, Universal Series Bus, USB, and serial ports such as Serial Advanced Technology Attachment, or SATA. Peripheral devices include mouses, keyboard, printers, monitors, even CDs are considered to be peripheral devices. Some devices are strictly input kind of devices, meaning they can only send information. Others are strictly output kind of devices, meaning they can only receive information and print something on the screen or play some kind of audio. For example, headsets. And then there are those who act both as input and output. So DVDs, for example, are peripheral devices that both accept data and can produce some data. The photo camera, for example, is another device that you use it to take pictures, and those pictures are stored and then displayed on the camera's display screen. And the telephone is another input-output peripheral device. You input a telephone number and then you communicate with the person on the opposite side of the line, and so on. There are many examples. Even the webcam is considered to be an input-output device. If that webcam has a microphone attached to it, then it receives information from the microphone, information in form of your voice, and then processes it, and so on. Peripheral devices, to continue our discussion about peripheral devices, input devices convert incoming instructions or actions from the user into variable information that can be interpreted by the computer. For example, a keyboard will convert keystroke into characters that appear on a computer's display, while a monitor will transform hand movement into movements of a cursor that can be used to interact with the operating system's programs. Other input peripheral devices include joysticks, microphones, webcams, optical scanners, etc. Output peripheral devices translate digital signals into information that can be interpreted or utilized by the end user. For example, a monitor or display screen will show the operating system's desktop, while a laser printer will translate information saved in a Word file into printed material. Other output peripherals include speakers, 3D printers, and projectors. Some devices can provide both input and output signals such as network interfaces, modems, routers, and webcams. And that's really the end of our discussion for today. So like I said, next time we get into the hardware communication part and software topology for instruction set. With that being said, thank you for your attention, and I will see you all next time.